So this time we want to do integration by parts when we have to do multiple application, and then we want to kind of build up the tabular method basically in there as well. So how do we start? Let's start with what we know is just application of integration by parts once, and that's the very first basically example that we started with. An example is antiderivative of x e to the x dx, right? So the choice of u and dv, we kind of figured out, well, I know how to antiderivative e to the x. I know if I take the derivative of x, it would be 1, and therefore I will end up in my second line by antiderivative of e to the x, basically. So what was the story behind it? I will go u equal to x, and then dv to be u to be x, dv to be e to the x dx, and then antiderivative x to derivative x to get dx, and then antiderivative that one to get v equal to what? E to the x. And then I knew that I have to multiply these two, then subtract the antiderivative of the second line. But this antiderivative of the second line is basically antiderivative of e to the x, because I ended up with 1 times dx in here, right? And so over here, if the second line, the antiderivative of the second line is just e to the x. So what happens is that, let's see, so I started with the x and I ended up with a 1, and then I went to a 0. Now I'm forming in this table. What do we say? We say that these two multiply together, and then minus this antiderivative of the second row, which would be basically just that 1 times e to the x. And so what do I get? I get this one, x times e to the x, and this one plus this one is minus e to the x, because you're subtracting, and the answer is x e to the x minus e to the x plus c. So even with one integration by parts, if you have this vanishing term, if you have a polynomial that you will choose as u, then there is a way to make it in the format of tabular. And so what I'm going to do is next present you an example that you have to use multiple application of integration by parts, and then make that into a tabular format, and you can compare how easier that can get. Again, integral is in here is x e to the x dx, and my first instinct is to choose u to be x squared, and then dv to be e to the x dx. In the hope of taking derivative will reduce the degree of x, and I know how to do the antiderivative of e to the x. But then when I do this, I get du equal to 2x dx and v equal to e to the x, right? At this point, if I write down the integral, I will end up with x squared e to the x minus antiderivative of the second line, which is 2x e to the x dx. Oh, do I know how to antiderivative this one? Well, in a way I do. I know this is going to be an integration by parts again. So if I write it clean, x e to the x minus, oh, we don't even need to write it clean, but I mean, you can take the 2 out if you want. Okay, so I have to do another set of u and v. This time, again, I'm not even going to write the u and v. I'm just going to put it in that order. And so this time around, I will have x, I'm sorry, yes, x. Let's keep the 2 in here so we can match that, actually. So let's have 2x and then have dv to be ex dx, and then take the derivative of x, you get 2. Over here, antiderivative, you get e to the x. If you want to match that, you know you have to take the antiderivative of the second line, and antiderivative of the second line is just going to be antiderivative of 2e to the x. So if I take the antiderivative of e to the x, this one is going to be derivative of that is going to be 0, and the entire thing is going to be these two multiplied together and minus these two. Now you have to replace that back for this, and then in this table, those are the first choices. This side is the dx, this side is antiderivative, and then you come and you go diagonally like that with multiply diagonally x squared e to the x, then you subtract minus 2x e to the x, then you add again, so you alternate between subtracting and adding 2e to the x, and then you add all these little product that you found, and that's your final answer. It's much easier doing it this way than to complete applications of integration by parts. And so it's very important if you have a polynomial of degree 5, a table is a lot neater and cleaner than what you do with 5 integration by parts every time choosing u and v and so on and so forth. Now, I want to show it with this integral. Let's see, I'm going to change the example a tiny bit. So my thing is that, again, with trig function, sine of something and cosine of something times a polynomial, I usually choose, for those, I always choose the polynomial to be u and the other part to be v prime, basically, or the other prime times part times dx to be dv. Now, write that down in a table. And so I have x to the third plus 1 on the left and sine of pi x on the right, and then take the derivative of this side until you hit 0. Remember, we went all the way to 0 over here, and so you get 3x squared, then I get 6x, then I get 6 and 0. So one more than that one. And then on the right, take antiderivative. Sine of pi x, it would be antiderivative of that is negative cosine of pi x divided by pi. Antiderivative of that is going to be negative sine of pi x divided by pi squared. Antiderivative of that is going to be positive cosine of pi x divided by pi to the third. Antiderivative of that is sine of pi x divided by pi to the fourth, basically. And now, so what you do is diagonally, this one is going to be a plus, this one is going to be a minus, alternating plus and a minus. And so what do you get? you get over here, and I'm running out of space, but here x to the third plus 1 negative sine of pi x divided by pi. Here, these two are multiplying together, and a negative times that negative makes it positive. 3x squared sine of pi x over pi squared. And then here, 6x positive cosine of pi x over pi to the third. Here is a negative sign, negative 6 sine of pi x divided by pi to the fourth. This x times the integral of x times sine and cosine represents the resonance in physics, basically. That's why it's important to learn how to do this type of integral. Now, I'm not done though. Let's just add them all together, basically, with the whatever sign that was enforced to them. And so what do I have? I will have, the first term was negative x to the third plus 1 times sine of pi x divided by pi. Then I will have, the second term was negative times negative was positive plus 3x squared. I apologize, the first one was cosine. The first one was cosine. The second one is sine over pi squared. Then you will have yes, this negative times negative, and then over here you had positive and 6x times cosine, so plus 6x cosine of pi x over pi to the third, and then the very last one becomes a negative again, negative 6 sine of pi x over pi to the fourth plus c. And so this is how it's much easier. You can try to do basically 3 integration by parts and compare with that. It's a lot nicer using the tabular method, and it's the chances of error decreases a lot, basically.